Okay, so this is a quick overview on the status on RISC-V support in easy. It's going to be very short, but I think it's worthwhile to discuss this because this is going to be very relevant very soon, I think. And it's also interesting to see what we can do here and what kind of impact we can have. Okay, so first of all, just to make it very clear, what is RISC-V? It's yet another CPU architecture, right? Next to Intel and AMD, which are x86 64-bit, ARM 64-bit, PowerPC, which were then RISC-V 64, so 64-bit RISC-V CPU are becoming very relevant for us. There's 32-bit as well, but that's mostly embedded, and I don't think we really care about that. RISC-V is what people refer to as open source hardware. So it's very different from Intel, AMD, ARM CPUs, where you basically either have to pay Intel. Well, for x86, that's a lost cause because it's only Intel and AMD who are allowed to produce chips, x86 chips. For ARM, it's a bit different. You can buy a license from them, and then you're allowed to design your own CPUs. But those CPU designs stay secret, so the companies don't release them. All the details on how the CPU is constructed and stuff is not shared. That can change with RISC-V. So with RISC-V, everything is done out in the open. All the standards are there out in the open, and you don't have to ask anyone permission even to design your own RISC-V CPU. You can produce them fully on your own, and you can share the processor design details. You don't have to. So companies who produce RISC-V chips often do, but strictly speaking, they don't have to. So that's not a given. There's a Swiss non-profit that is pushing RISC-V, so defining the standards and doing community events and all these kind of things. They used to be US-based. They deliberately switched to Switzerland to be neutral and not be subject to US export regulations and things like this. So they're being very careful also from a legal point of view to make sure that everything is indeed open to everyone. Originally RISC-V was mostly focused on embedded computing, so like smart devices. If you have a thermometer that probably has a small RISC-V chip in it, like there's RISC-V around all of us, but we never see those chips. So they're very prevalent already. But that's changing fast. So it's breaking into more general purpose computing, and it's also breaking into HPC. So yeah, there's already pretty good support in standard Linux distributions, Fedora, Ubuntu, all of those know about RISC-V, support RISC-V, build packages for RISC-V, and so on. C has good support for it, probably LLVM as well. So it's certainly not new in that respect. Now, why should we care about RISC-V? Well, and it's coming fast, and it's going to be hard to ignore. I think if you miss that train, it's going to be a problem. And let's say 5 years from now, we'll have actually capable RISC-V hardware. That's not there today, but there's lots of projects. There's actually quite a bit of European money going to projects in terms of developing the RISC-V ecosystem, software, hardware, research, building up knowledge, building up expertise. That's going quite fast. There's quite a bit of money going in. One example of that is the European Processor Initiative, where the explicit goal is to develop a CPU that is entirely designed and manufactured in the EU, so without having Chinese or American companies involved, and basically making sure we are self-sustaining for our CPU. That's sort of the end goal of this project, and they're ramping up to that via ARM and RISC-V accelerators, and then the RISC-V actual host CPU and so on. So there's a long road ahead there, but that's sort of the end. There's lots of other examples of European projects in this scope as well, and especially the Barcelona Supercomputing Center is very active in this context. That's capable hardware is not there yet, but stuff is definitely coming. People are designing RISC-V CPUs, including with vector extensions. So that's a new addition to the standard. That's since a couple of months, it's actually in the RISC-V standard. That's of course very relevant for HPC vector instructions. There's now actually a very interesting Kickstarter for an SBC, a single board computer, with a RISC-V CPU, something that's capable enough that you can actually do stuff with it. So it's 8 GB of RAM, has 4 cores. It's basically a Raspberry Pi that's ARM, but for RISC-V. So that Kickstarter is still open for another couple of days. You can get a 4-core, 8 GB board for about $100. So it's very affordable. If you just want a nice toy to play with, you can sign up for that. And I did, and I know several other people. There's already a special interest group in the RISC-V community specifically for HPC. So they have helped with designing or writing down that vector extension standard. They're starting to organize sessions at ISC and SC, so the big supercomputing conferences specifically for RISC-V, to make the community aware that this thing is there, it's coming, and you better pay attention if you don't want to miss it. There's big companies. Intel has some kind of developer environment for RISC-V, so even the big CPU companies know that they have to pay attention and be active in that community. And NASA recently announced that they're going to be using RISC-V CPUs in basically all their future space missions. So they're getting rid of the now ancient CPUs that they're using, and they're going to probably design their own CPUs fully open. That's a nice development. So in easy, this is all a bit of an opportunity, right? Because we can, like, through emulating RISC-V CPUs and building in that environment, or using these basically toy computers, we can start building software for RISC-V, scientific software, see what works, see what doesn't, see what has to be fixed. People are already playing with MPI on RISC-V boards and playing with InfiniBand on RISC-V boards, so that's already happening now. So there's a lot of interesting. We can probably surf that wave and yeah, get some attention. Now, what needs to be done to support RISC-V and easy? There's three things, the 3 different layers. So first of all, is getting CVMFS to work on RISC-V, only the client side. So we're not, at least for now, we're not interested in running the CVMFS server on RISC-V. That doesn't really matter. Just as a client, as a laptop, or as an HPC system, you need to be able to connect or to mount our repository. So just the client side is okay. This should actually already work, but the last time it was tested, I was told by the CVMFS developers, was 4 years ago. So when one of these first boards came available, the lead developer bought a board and played with CVMFS a bit on there, compiled it, and it seemed to be working fine. But other than that, they haven't really been tested. But at least it's good news. There don't seem to be any blockers there. And if something pops up, it's probably easy to. Then climbing up in the ladder, the compatibility layer, so that was a bit of work. Gen 2 Linux itself already had good support for RISC-V. They're building packages for RISC-V, they're testing that. What didn't work yet was bootstrapping Gen 2 prefix, so having a Gen 2 installation in /CVMFS, so in a non-standard prefix. We had the idea to write out a Google Summer of Code project for this year, and we found a very good Indian student who jumped on this, who worked on this, was very enthusiastic, and basically fixed all the problems that you would hit when bootstrapping Gen 2 prefix on RISC-V, and also testing packages that we need in easy to get RISC-V supported in our compatibility. So we haven't actually tried building a compat layer for RISC-V yet, but we should be able to. As far as he could tell, all the bits and pieces are there, everything is working. That should work. Now, one thing we do want to have there is our build container, Debian 10 Singularity container image. We want to have that for RISC-V, so we have the same controlled environment as we have for the other CPU architectures. If Debian 10 doesn't work, we can switch to another OS. The OS itself doesn't really matter. It's mostly about having a container and a controlled environment. That's maybe something we need to look at, and then see if we run our Ansible playbook for installing the compat layer, how far do we get and hitting any walls there. Singularity already works on RISC-V, so that's not an issue. And then when those two are done, and they can actually be done in parallel, just to make sure that things work, we can start looking at the software layer as well. EasyBuild is already aware of RISC-V. It has some recent pull requests that got merged, like for binutils. We have a small exception there. Left and right, we already have stuff. We didn't get very far yet, so I don't think building GCC with easy build on RISC-V currently doesn't work. It's probably an easy thing to fix once you know what needs to be changed. It's not going to be a lot of work, but there's some bumps in the road. The good news is MPI, Open Blast, so all of these components should already work on RISC-V as well. So most of these stuff have been already tested. So yeah, the groundwork is done in some sense, and we can take the next step. Yeah, so that's something. It's certainly not a main goal of EASY currently, but it is also a part of the multi-xscale project, which we'll talk about tomorrow. So it's something we'll at least be paying attention to on the side, and whenever we see an opportunity to do something there, we probably will. But maybe future Google Summer of Code projects, maybe specifically to EASY on this, because there's, especially in Asia, there's quite a bit of activity and interest in RISC-V, so maybe we can surf that wave a bit. Yeah, and that's what I have.